This is a computer model, a digital representation of an object. However, this is no simple computer model. This is a model that revolutionized various fields of science forever. This is a model that made computer models. This is the Mandelbrot set, a forever repeating shape called a fractal. This was no simple feat. It was a lifetime's worth of innovation and curiosity that led to the creation and establishment of the field of fractal geometry and computer modeling. And we have one man to thank for it, Benoit B Mandelbrot. In the 1950s and 60s, computing was quite different from what we know today, with a mix of mechanical devices, punch cards, and early digital computers that had limited power and capabilities. This era, prior to Benoit B Mandelbrot's contributions, were foundational in the development of model computing, but still largely focused on problem solving in scientific, military, and business situations. These computers were incredibly slow by today's standards and could only perform simple calculations, usually at a pace of a few thousand operations per second. Before Benoit B Mandelbrot's work on fractals in the 1950s, 60s, and 70s, graphical output from computers was non-existent. Most computers were focused on numeric calculations or generating simple charts using basic plotting techniques. The computer power available in the 50s and 60s could handle relatively small-scale simulations of physical systems, but due to the limited processing speed, the models were less sophisticated compared to today's computational simulations. 1970 saw the introduction of an electronic graphic device with an attached photographable screen. Mandelbrot was one of the first to publish pictures created from this machine and used the opportunity to create pictures of fractal mountain landscapes, like the one behind me. Before this, he had to use a typewriter to print a combination of letters on every point within his 64 by 64 grid in order to construct the first computerized model of a fractal. He and his team of programmers became renowned for their perseverance against the restrictions of technology at their time. He even helped to develop the initial software that colorized computer graphics. He created a successful simulation of an infinitely repeating object that had only been seen thus far in nature. Snowflakes, leaves, snail shells, coastlines. We are surrounded by fractals in the natural world. But who was Mandelbrot? He was a scientific maverick. He saw the forever repeating sequences in the world around him and made it his goal to understand it. Not just for himself, but for the greater good of society as a whole. Benoit B Mandelbrot was born in Warsaw, Poland in 1924, born in between the two world wars. He grew up with both of his parents who loved him dearly. He claims to have grown up in a house of mathematicians, surrounded by rigorous academic discussion and innovation his entire life. The cornerstones of his life were his parents, his uncle Solom, and his wife Aliette. His uncle Solom was a famous mathematician in his own right, known for his research into mathematical analysis, and was a beloved mentor to Mandelbrot. Unfortunately, Mandelbrot and his family were forced to leave their community behind during World War II due to their Jewish and Polish identities they felt deep pride in. They sought refuge in Paris, France, with his uncle Solom. Shortly after finishing his secondary school education, Mandelbrot left France for his undergrad. In 1950, he returned to pursue his PhD at the University of Paris. He struggled with his dissertation topic, often taking time to read a variety of books from differing fields. His uncle Solom disapproved of this discovery process, citing it as a waste of time. He often scolded Mandelbrot for this, but in a twist turn of events, Solom gave Mandelbrot one more book to mess around with, under the condition that Mandelbrot will finally focus and pick a dissertation topic after this. The final book was by George Ziff, a man who studied a field of his own creation called statistical human ecology. This field can be compared to modern fields of computational social sciences, where statistics and big data ideas are applied to social science and human studies research. Within this field, Ziff created a law that he claimed to be a universally valid summary of a mass of empirical observations on how the words in ordinary writing are distributed between common and rare. Or, in other words, this law would be able to describe the frequency of word use in any literary writing. Right in between his PhD and postdoctoral, Mandelbrot was riding the metro to hang out with his Uncle Solom. On the way over, he read the literature on Ziff that Solom had given to him. As he read, he realized that Ziff's law could only be used for a general range of literature. Mandelbrot adjusted the formula of Ziff's law so that it can be used for any piece of literature of any conceivable length. This became the Ziff-Mandelbrot law. It is now applicable to fields outside of linguistics, such as statistics and physics, due to the reformation of the law. This is what Mandelbrot called his first Kepler moment. A critical turning point in his life, he had achieved his dream and was hungry to achieve bigger and bigger dreams. Many more were such moments were to come. He got a taste of discovery and went on to garner a buffet of innovation to consume. In France 1945, there existed a rigorous exam for students to get into one of two prestigious science French universities, École Normale Supérieure and École Polytechnique. Mandelbrot did so well on this exam, he qualified for both universities. After much internal debate within his family, he decided to pursue his education at the École Polytechnique, also known as Carva. He studied there for 2 years and graduated with a BS. It was here where he found professors whose findings contributed to his own discoveries heavily. Professor Gaston Julia and Paul Levy. Gaston Julia was, as Mandelbrot described, a scientific maverick taken for granted. He is best remembered today for his discovery of iterating rational functions, or his Julia set. Julia sets are the graphical representation of all possibilities of complex numbers existing within a certain range. When you graph every point of a Julia set, you draw out a picture of a fractal. But how does this occur? Let's build one together. We begin with defining a complex number and imaginary numbers. Typically, when we think of numbers, we are thinking of real numbers. These numbers include 1, 2, 4, pi. All rational and irrational numbers are real numbers. However, real numbers have limitations. There are just some problems that real numbers just can't solve. One such important problem was that of the square root of -1. You have been taught that such an equation is impossible to solve, but that's not quite the whole truth. The square root of -1 was an unsolvable problem for hundreds of years due to the limitations of the real number line. In order to solve this problem, we must use a different number system. This system allows us to solve the problem with a solution of I squared equals -1. But where is I? I lives in the imaginary dimension. This dimension, contrary to its name, is a real dimension that exists as a rotation of our current number line. Imagine you can rotate upwards on the real number line. That is where I and all of its buddies live. So why does this matter? Now we can combine real numbers and imaginary numbers to create complex numbers, such as 3 plus 5i. The general format of complex numbers we will use is x plus yi. Julia comes in with a way for us to add these number combinations to then do meaningful math with them. Let us begin with z. Z will be equal to x plus yi, where x and y represent coordinates within the imaginary grid. We can square z so that it becomes a real number, giving us z squared. Z squared can now be added to another complex number in order to give us another coordinate to plot on our graph. Now we have z squared plus c for complex number. Continually Doing this process for infinity will give us the answer of the previous equation and adding it to C to create a graph that has an eerily silly shape. Hey, wait a second. This looks really familiar, doesn't it? It should. Julius sets are fractals. Mandelbrot was the one who came to this recognition and wielded his new computer modeling skills to create the infinite representations that just couldn't have been made in Julia's time. Mandelbrot then added upon this set by mixing up the formula a bit. Instead of C being the same complex number every time, he changed it so that every new addition to the graph had a differing C. In doing so, Mandelbrot created an image that represented all possible shapes of a Julia set. He found a way to visualize a shape that had long ago been described but only ever been seen in nature. This is his most memorable discovery, his transformation of fields. I introduce to you the Mandelbrot set. As you zoom in, you can see a new fractal shape emerging from the one before it. And if you zoom in enough, you will see the beginning of the shape appear over and over and over, eternally recurring with the power of Mandelbrot's computations. Carva didn't just provide to Mandelbrot his famous imagery, but provided to Mandelbrot the understanding of where this image lies within our mathematical realms via Levy's teachings. What dimension does this thing show up in? You may be inclined to say that this is a two-dimensional representation. After all, aren't these just dots on a graph? Well, recall that the graph is in an imaginary dimension. We're going to investigate just what this imaginary dimension is in order to bring a little reality into it. First, probability has existed as a concept for a very long time. There was a missing component that statisticians' calculations could not go over. Time. In real life, events don't happen in isolation of each other. Events, such as the probability of you getting to school on time, sometimes depends on other events happening before it, such as you waking up to your alarm. Levy tackled this with his own process of calculating probabilities with respect to time. This allowed for new ideas of dimension to arise, such as imaginary dimensions. Mandelbrot's imaginary fractional dimension was not created alone. Rather, it was a collaboration of his own work alongside Paul Levy's and a graduate student named Henry McKean. McKean's own work involved applying Levy's work on time processes to the fractional dimension referred to as the Hausdorff-Besicovitch dimension. A fractional dimension object is more than one-dimensional, but less than two-dimensional. So, fractals are these funky shapes that live in an in-between dimension. This is the realm of Hausdorff-Besicovitch. This dimension is denoted D by Mandelbrot. A second dimension is important to fractals. This is the topological dimension. This refers to the coordinates of where an object is in space and how complex it is. An object with a topological dimension of 1 would be a straight line with a point to describe its position. In the picture shown, we can observe the pole becoming more complex and thus taking more space. We now need more coordinates to describe where these trees are in space. This can grow until the maximum of 3. Where the object requires the most coordinates to describe its location, X, Y, and Z. So, fractals have two types of dimensions that describe them. There is the description of how complex the object is, D, and there is the description of where in space this object exists, known as DT. Knowing this, we get to do something very cool. We can mathematically define a fractal. Mandelbrot combined everything we just talked about to come up with this definition of a fractal. A fractal is a shape where D is greater than dt, or a fractal is a shape that is more complex than can be described with its location in space alone. A fractal is a complex and never-ending shape, yet it has a concrete address for us to point at and say, there it is. Benoit B Mandelbrot was an extraordinary man whose contributions of extraordinary discoveries and theories to dozens of scientific fields will long outlive him. But where exactly do we see this legacy today? In what fields do investigatory elements include fractals? Well, one prominent place to search for fractals is in nature itself. Fractals and the larger field of fractal geometry is a way of describing patterns that naturally occur around us every day. They are models of description. One such example is coastlines. Imagine yourself spending a day on the beach. Imagine the smell of the salty seawater hitting your nose as you walk along the soft sand. As you are walking, you may wonder to yourself, how long is this beach? As you begin, you notice a problem. The boundary between the water and the sand is not a straight line, so you'll have to figure out how to estimate the measurement precisely. You can use fractals to estimate the length. You can begin with a general shape and the coastline to describe its length. However, this length isn't quite accurate, and many corners and turns are missing. So, you must complicate your shape to get a more accurate estimate of the beach's length. Fractals can be superimposed on top of coastlines as a way to determine its complexity via its D dimension value. Now, much like the coastline itself, we have a shape that is finitely infinite and has flexible levels of complexity that we can use to measure. Mandelbrot did this with the coastline of Britain, where he used general estimates of the coastline to create a fractal equation to represent it. Through this, he discovered that the coastline of Britain has a dimension D of about 1.25, or the coastline of Britain is slightly more complex in shape than a standard curve is. The higher the dimension, the more jagged and crazy the coastline is. The lower the dimension, the more straight and smooth the coastline is. This example of coastlines is a visualization of the type of model description researchers use fractals for, as well as helping with the analysis of the land. Mandelbrot and his fractals will live amongst the legends of mathematics for decades to come. His visionary approach to exploring patterns in nature through the lens of mathematics not only introduced the world to the infinite beauty of fractals, but also laid the foundation for the development of modern computer models. His perseverance in overcoming the technological limitations of his time, combined with his relentless curiosity, led to revolutionary advances in fields ranging from economics to medicine. One can say that his contributions to science would outdo that of his model, Johannes Kepler. He was an astronomer and mathematician from the 17th century who discovered the three laws of planetary motion. His discovery revolutionized physics as a field of study at the time. Mandelbrot felt deeply inspired by this and made it his own life mission to discover something at the intersection of sciences, just as Kepler did. As Mandelbrot pursued the solutions to some of the biggest scientific challenges of his time, he discovered more problems in their place. He, like his fractals, maintained a cycle of ever-infinite repetition of discovery and complication. His work emphasizes the importance of looking beyond conventional boundaries, embracing complexity, and not allowing others to shame you from your journey. His belief that science is about discovery encourages future generations to continue exploring the uncharted territories of science. His attitude of discovery is representative of his attitude of science altogether. It is already invented, it is just waiting to be discovered. His legacy will continue to inspire generations as the generations before him inspired him.